Welcome to this presentation on the design and construction of a low-cost, modular, single-axis solar tracker. Here is a list of topics that we are going to cover. One of the main reasons for tracking is to increase efficiency. The tracker will keep the solar cooker aligned to the sun as the Earth rotates. The estimated increase in efficiency is between 20 to 35%. Once tracking is available, the solar cooker can be left without attendance from the cook. When using solar dehydrators, where the food is left all day, a tracker will increase the speed of drying. It also allows the user to leave it unattended all day. Similar benefits are available to beekeepers who use solar beeswax extraction. In all these applications, it's important that the cost and complexity of the tracker is kept low. We think that we have achieved this with our design implementation. Note: without Stan Wells' help and guidance, this venture would not have been possible. There are a number of different design approaches to implementing solar tracking. Some of these are listed here. On average, the sun moves approximately 15 degrees per hour across the sky. This is 360 degrees divided by 24 hours. With a mechanical tracking system, a clockwork mechanism is used to move the parabolic dishes at the rate of 15 degrees per hour. The dishes rotate continuously to follow the movement of the sun, always concentrating the solar rays on the receivers. Every morning, the dishes are turned manually to line up with the position of the sun, after which the automatic tracking takes over. The photo shows an array of 73 dishes, on top of a Sai Baba temple in India. The steam created is piped into the kitchen and used to prepare meals for 25,000 to 30,000 devotees. A passive solar tracking system uses thermal expansion or gravity-based mechanisms to adjust the position of solar panels or mirrors without motors, sensors or electronic controls. In the system shown, the sun's heat moves liquid from side to side. As the sun moves, the rack follows, at approximately 15 degrees per hour, continually seeking equilibrium as liquid moves from one side of the tracker to the other. This action allows gravity alone to turn the track rack to follow the sun, therefore no motors, no gears and no controls to fail. The track rack also features an early morning, rapid return system. Solar tracking using astronomical methods involves precisely calculating the sun's position relative to a specific location on Earth at various times throughout the day and year. This relies on astronomical equations that account for factors such as latitude, longitude, time of day, and the Earth's axial tilt and orbital dynamics. By determining the sun's azimuth, horizontal angle, and elevation, vertical angle, solar trackers can optimize the orientation of solar panels or other devices to maximize exposure to sunlight, improving energy efficiency. Active tracking uses sensors like light-dependent resistors to detect sunlight intensity and adjust position accordingly. Motors and microcontrollers are employed to move the cooker in real time. We decided to follow the active tracking route, as it was simple to implement, lent itself to a modular design, and was of low cost. Tracking along the vertical axis is where the tracker follows the sun east to west, that is, the azimuth of the sun. Horizontal tracking is required to follow the elevation of the sun. Single-axis tracking is much easier to implement and results in a lower cost. The question was, does dual-axis tracking add much to the performance of a solar cooker? Here is elevation and azimuth data for London on the 1st of June, from 9 a.m. to 3 p.m., using the SunCalc website. Calculating the standard deviation for the elevation shows that, if one fixed elevation of the cooker at around 52 degrees, at the worst case, this would be less than 10 degrees off the optimal. However, if one did not track the sun east to west, the azimuth will be almost 50 degrees off the optimal. The figures for different times of year for London show a similar finding. Based on these figures, we decided just to track the azimuth and leave the elevation fixed over the cooking period. Here are the key components of the tracker. The motor chosen for the job is shown here, along with mounting and flange coupling. It has a gear ratio of 3000, resulting in a high torque of 30 kilograms per centimeter. The insides of the worm gear motor is shown in this photo. This motor can easily be driven at 9 volts, and, because of the gearing, only takes 10 milliamps when operating. It rotates very slowly at 0.6 revolutions per minute, which in our application is not an issue at all. The low speed, high torque and very low power consumption makes this motor ideal for turning a heavy solar cooker into the sun. The sensors chosen for this active tracker were 2 small solar panels at right angles, as shown in this photo. They are wired such that, when they are pointing exactly at the sun, the voltages they produce cancel each other and the result is 0. However, if one panel receives more sun than the other, then there is an imbalance, and a small voltage is produced. This voltage is used by the electronics to move the motor, until there is no voltage. At this stage, the 2 sensors are pointing exactly back at the sun again. Because of the low power required by the motor, it can easily be driven from a 9 volts PP3 battery. The one we used in our design was a lithium battery, with a built-in USB charger. With a capacity of 1,300 mAh, it can easily deliver more than 100 hours of operation between charges. The electronics used to check the output of the sensors and drive the motor is shown here. It uses a PIC microcontroller, as this gives much greater flexibility compared to just using analog comparators. Full design details are provided on the website www.sfinnovations.co.uk. This includes schematics, software listings, and information on where to source the components. The wooden platform can be made to a size to suit the solar cooker. The drive wheel used was made of wood and lined with rubber to give it good traction. It seemed to work equally well on grass and concrete. The motor and wheel can be placed to the front of the platform or the rear. 2 suitable sized casters were used at the opposite end. The sensors were placed on the outside of the enclosure, used to house the electronics and battery. On one tracker, the box and sensor was mounted on a wooden stake, the top of which was angled. On the other, we used a metal bracket to fasten the box to a long wooden stake. This brief presentation outlines the design and construction of a low-cost, modular, single-axis solar tracker. It allows the user to maximize the efficiency of their solar cooker or dryer, as well as freeing them up from constantly readjusting to follow the sun from east to west. Full design and construction details are available on www.sfinnovations.co.uk.